In this lecture, I am going to have discussions on Laplace transform of a linear system, transform from S domain to Z domain, delay property of G transform, and transfer function of a linear system. This is the copyright information. Fourier transform generally deals with the sinusoids. On the other hand, Laplace transform deals with both the sinusoids and exponential signals. That means Fourier transform is a subset of Laplace transform, or Laplace transform is a general form of Fourier transform. Fourier transform of a system can be expressed by this equation. In this equation, a time domain signal x of t is transformed into a frequency domain signal x of omega. It is possible to expand this Fourier transform into Laplace transform through some modification of the equation. This is the Laplace transform of a time domain signal x of t. In this equation, a time domain signal x of t is multiplied first by an exponential term before the transformation. This equation can be rearranged further, and sigma plus j of omega can be assumed as S. This equation represents the Laplace transform of a continuous signal x of t. S-plane is continuous, which extends up to infinity in all four directions. Laplace S is a complex frequency, which is expressed through this relation. Response of a linear system can be found under any types of excitation using Laplace transform. Some examples are shown here, such as switching on and off at any given time instance, sinusoidal input, impulse, or square wave. It can be summarized that Laplace transform deals with both steady state and transient response of a linear system. It allows complex frequency, and it is a generalization of Fourier transform. Now let us find out how Laplace transform can be changed into G transform. It can be done by changing the continuous signal to discrete signal. Equation for G transform, which is shown here, is obtained by changing the time variable t in sample number n and by changing the integral to summation. Now let us assume r equal to e to the power sigma and z equal to r times e to the power j omega. After replacing these values into this equation, G transform of the discrete time signal x of n becomes as the summation of these two terms from negative infinity to infinity. This is S-plane shown in rectangular coordinate. This is real axis. This is imaginary axis. This is G plane represented in polar coordinate. This is the unit circle of radius 1. R represents distance from the origin, which is related to the exponential decay. Omega is the frequency, which is measured from the positive horizontal axis. In this equation, notice that the G transform uses parentheses, which indicates that x of G is continuous and not in discrete form. In case of S-plane, left side of this imaginary axis, shown in green color, corresponds to the interior of unit circle in G-plane. These regions are stable regions. In these regions, impulse response of a system is stable. Right side of the imaginary axis, shown in red color, corresponds to the exterior of unit circle in G plane. These regions, shown in red color, are unstable regions. In these regions, impulse response of a system is not stable. If a time domain signal is completely real, these lower halves and upper halves are the mirror images of each other. Well, these points have been discussed in the last slide. These are the DC points where the impulse responses of a system have zero frequency and the impulse response neither grows nor decays over time. This point corresponds to Nyquist frequency. This point shown in purple color corresponds to the line where the impulse responses neither grows nor decays over time. But the frequencies along this line keep increasing from DC point. Points shown in yellow color are identical to the points shown in purple color, but they indicate negative frequencies. The points shown in blue color correspond to the line where the impulse response increases over time. And along this gray line, impulse response of a system decays over time. These points along this green line correspond to the points of constant frequency. If the point crosses the unit circle, then the impulse response of the system becomes unstable. Let us consider a time invariant system with impulse responses of 5 discrete values. The amplitudes of the samples are shown in this plot. G transform of the system can be found out by expanding this equation, which can be expressed in this form. This equation can be simplified further and can be expressed in terms of polynomial in G to the power minus 1. Input-output relation of a linear system can be expressed in terms of transfer function. Transfer function of any system, as shown in this figure, is the ratio of the G transform of the output and input signals. After rearranging this equation, G transform of the output can be expressed as the product of the transfer function and G transform of the input. Now let us investigate the delay property of a linear system. As it was explained before that, the G transform of a discrete time signal x can be expressed by this equation. Similarly, G transform of a time delayed signal x of n minus I can be expressed by this equation. Now let us assume P equal to n minus I. Putting P in this equation, the equation can be written in this form. Taking G to the power minus I outside of the summation sign and further simplification, G transform of this time delayed signal by I samples become G to the power minus I times x of G, where x of G is the G transform of x of n. From this observation, it can be stated that if a signal is time delayed by I samples, its corresponding transformation in G domain can be expressed as the product of G to the power minus I and x of G. A time delay of two samples in time domain is equivalent to G to the power minus 2 times x of G in G domain. Consider an example of unit delay. This is the representation of the system. Here del of n minus 1 is the impulse response. Since the output of the system will be delayed by one sample, transfer function of the system can be represented as sum of del n minus 1 times G to the power minus n. After simplification, the system transfer function becomes G to the power minus 1 times del of n. Since the value of del of n is 1, h of G becomes G to the power minus 1. This block represents the system. Output from the system is the delayed version of the input by one sample. Consider an example where time domain input is composed of 7 discrete samples. Here are the values in the first row are the sample numbers, and the values in the second row are the corresponding amplitudes of the signal. Since the system is an LTI system, any values of the signal before time instant 0 is also 0. This is the plot of the input samples. Now the G transform of the input can be expressed in this form. This equation can be simplified further and be written in this form. Now consider another example of unit delay. This block represents the system where impulse response is Z to the power minus 1. Input samples in time domains are given. Using the transfer function relation, G transform of the output can be found out from the equation Replacing the value of h of g, x of g can be found out from these time domain samples. Therefore, y of g can be expressed in this form. After simplification, this is the final form of y of g. Now, the output y in time domain can be found out by taking the coefficients of the right side of this equation. These are the output samples in time domain, and this is the plot. This is the reference book for further reading. At this point, I would like to have an end of this lecture.